Today, we dive into a mystery that's baffling the brightest minds in physics. Imagine a colossal machine buried deep underground, stretching across countries, with the power to recreate conditions just moments after the Big Bang. This is CERN's Large Hadron Collider, the world's largest and most powerful particle accelerator. But what if we told you that something went terribly wrong? Recently, an unexpected and inexplicable event occurred at CERN, leaving scientists scrambling for answers. Actor and science enthusiast Terrence Howard shared his insights on the LHC's latest developments, offering a unique perspective on the ongoing discoveries and challenges. The anomaly observed has stirred a whirlwind of speculation, theories, and excitement within the scientific community. What could have caused such a shocking outcome? And more importantly, what does this mean for the future of particle physics? Stay tuned as we unravel the enigma surrounding this perplexing incident at the LHC. Terrence Howard recently brought attention to a perplexing incident at the Large Hadron Collider, LHC. When CERN scientists pushed the collider to its highest energy levels, they observed an unexpected and puzzling result. Howard highlighted the excitement and speculation within the scientific community as experts proposed various theories to explain this anomaly. This unexplained result occurred when the LHC was operating at its maximum capacity. The observed data did not match predictions, leading to a flurry of activity among physicists. The anomaly has sparked numerous hypotheses, ranging from potential new particles to undiscovered principles of physics. Howard noted that the scientific community is buzzing with theories to explain this surprising outcome. Some experts suggest that the anomaly could indicate the presence of new, previously undetected particles. Others believe it might point to limitations in the current models of particle physics, suggesting that our understanding of the universe's fundamental forces might need revisiting. The implications of this anomaly are profound. If the observed result leads to the discovery of new particles or forces, it could revolutionize our understanding of the universe. Such a breakthrough would open up new avenues for research and potentially lead to the development of novel technologies based on these newfound principles. What caused such a surprising outcome? And what does it mean for our future scientific endeavors? These questions are at the forefront of the ongoing investigation at CERN. The unexpected results challenge scientists to think creatively and explore beyond the established boundaries of physics. The unexplained anomalies at the LHC highlight the ever-evolving nature of scientific discovery. As researchers delve deeper into the data and refine their experiments, the potential for groundbreaking discoveries grows. Terrence Howard's spotlight on this incident underscores the importance of continuous inquiry and the excitement that comes with pushing the limits of human knowledge. The scientific community, fueled by curiosity and driven by these unexpected findings, is poised to unravel more mysteries of the universe. Howard described the Large Hadron Collider, LHC, as a colossal machine, stretching across 2 countries and extending deep underground. Imagine a device so immense and powerful, it redefines our approach to particle physics, he explained. The LHC is not just a machine, it's a marvel of human ingenuity and engineering. Spanning a 27-kilometer ring, it lies beneath the border between Switzerland and France. This enormous structure is composed of superconducting magnets and a series of accelerating structures designed to boost the energy of particles. The sheer scale of the LHC is staggering, representing decades of collaboration among thousands of scientists and engineers from around the world. Howard highlighted how the LHC redefines our approach to particle physics. Traditional methods of studying the universe's smallest components were limited in scope and power. The LHC changes this by allowing scientists to collide particles at unprecedented energies. This provides a glimpse into conditions that existed just moments after the Big Bang, offering insights into the fundamental forces that govern the universe. The construction of the LHC is a testament to what humanity can achieve when united by curiosity and a quest for knowledge. The machine's development required innovative solutions to overcome numerous engineering challenges. From the design of its powerful magnets, which must operate at extremely low temperatures, to the precise alignment of its components, every aspect of the LHC represents the cutting edge of technology. Howard also touched on the captivating stories behind the LHC's creation. The journey to build the collider involved overcoming geopolitical, financial, and technical hurdles. It required international cooperation on an unprecedented scale, with scientists and engineers from over 100 countries contributing their expertise. The stories of persistence, collaboration, and innovation are as compelling as the scientific discoveries the LHC aims to make. More so, the LHC holds the promise of groundbreaking discoveries. It is designed to answer some of the most profound questions in physics. What is the nature of dark matter? What happened in the first moments of the universe? Are there additional dimensions beyond the ones we perceive? By smashing particles together at near-light speeds, the LHC creates conditions that allow scientists to probe these mysteries, potentially revolutionizing our understanding of the universe. CERN, the European Organization for Nuclear Research, stands as a beacon of international collaboration and scientific curiosity. Its origins trace back to the post-World War II era. As Europe was recovering from the devastating conflict, there was a growing consensus among scientists and policymakers that collaboration was the key to rebuilding the continent's scientific prowess. In 1950, the renowned physicist Louis de Broglie proposed the creation of a shared European laboratory to rekindle scientific innovation and strengthen peaceful cooperation. Soon after, in 1952, 11 countries came together to sign the CERN Convention, establishing the organization. By 1957, CERN was officially up and running on the border between Switzerland and France. CERN's mission has always been to delve into the mysteries of atomic nuclei and their components. To do this, particle accelerators were essential. These massive machines accelerate particles to nearly the speed of light and smash them together, revealing the fundamental building blocks of the universe. By the 1980s, the vision for the LHC began to take shape, driven by the need for a more powerful tool to explore deeper into matter's secrets. The LHC was designed as the world's most powerful particle accelerator, featuring a 27-kilometer ring of superconducting magnets and detectors. Its construction began in 1998, a massive project that brought together thousands of scientists and engineers from around the globe. Situated 100 meters underground, the LHC was strategically placed to avoid the complex terrain of the Jura Mountains and to shield it from external influences. This underground location also avoided the high cost of surface land. In 2010, the LHC achieved a major milestone by successfully colliding particles at an energy level of 3.5 tera-electron volts per beam, an unprecedented feat at the time. After subsequent upgrades, it now operates at an even more astounding 6.5 tera-electron volts. Picture two beams of particles racing at nearly the speed of light and colliding head-on. That's the extraordinary capability of the LHC. There are 4 key collision points within the LHC, each surrounded by sophisticated detectors designed to capture and analyze the phenomena resulting from these high-energy impacts. Most of the time, the LHC is busy colliding proton beams, but once a year, it switches gears to collide heavy ions like lead, creating a special annual event. Howard passionately conveyed the significance of these endeavors. Why invest so much effort? Because the quest to understand our universe drives us to push the boundaries of science and technology. Physicists are utilizing the LHC to explore some of the most complex theories in particle physics. They are particularly interested in studying the elusive Higgs boson and investigating a large array of particles predicted by supersymmetric theories. Hadrons, tiny subatomic particles composed of even smaller quarks, are a key focus. These particles form the building blocks of protons and neutrons. The LHC, named for its ability to collide hadrons, produces byproducts that often exist only briefly and can't be studied by any other means. Each collision in this enormous underground ring is akin to a mini Big Bang, offering scientists a glimpse into the fundamental components and forces of the universe. Constructed between 1983 and 1988, the LHC's underground tunnel spans a massive 3.8 meters in width and is protected by concrete. Above ground, there is a building housing essential equipment such as control electronics, compressors, ventilation systems, and cooling devices. The LHC generates around 15 petabytes of data annually, an immense volume of information. To manage this, an international collaboration created a specialized computing grid just for the LHC, which is a technological marvel on its own. The primary mission of the LHC is to uncover the secrets of the Higgs boson, a particle long theorized by scientists, but never observed due to its high mass. The LHC's powerful capabilities were designed to produce multiple Higgs bosons each minute, like setting a trap for an elusive creature. Beyond the Higgs boson, the LHC has delved into other uncharted areas of physics, searching for supersymmetric particles and other unknown phenomena. However, the journey hasn't been without challenges. Shortly after its launch in 2008, a magnet malfunction caused significant damage, delaying operations for over a year. But from 2009 to 2013, the LHC made groundbreaking discoveries, including finally observing the elusive Higgs boson. After its first successful run, the LHC was upgraded and resumed operations in 2015, embarking on new scientific adventures. The second run of the LHC lasted from 2015 to 2018, followed by another pause until it restarted in April 2022, with an enhanced beam energy of 6.8 TeV. This third run will continue to captivate scientists until 2026. During this third run, something extraordinary occurred on July 7th. A mysterious crack appeared in Earth's magnetic field, remaining open for an astonishing 14 hours. This allowed a surge of solar winds from the sun, resulting in massive geomagnetic storms and spectacular auroras. The crack was attributed to a co-rotating interaction region, CIR, from the sun, where solar winds of different speeds interact, creating turbulent plasma structures. Experts assure us that such cracks in the magnetic field are not unusual and usually close quickly. However, recent events show they can stay open longer, allowing some space storm energy to penetrate and potentially disrupt satellites, radios, and power systems. While our magnetic shield generally protects us from these storms, some energy occasionally slips through, similar to living in a house with a drafty window during a storm. Overall, the LHC continues to be a pivotal tool in uncovering the mysteries of our universe, with each run promising new discoveries and insights into the very fabric of existence. The LHC's operation involves not just incredible physics, but also managing vast amounts of data. Imagine a room packed with complex control electronics, compressors, ventilation systems, and cooling equipment. This high-tech environment is necessary to support the LHC's functions. However, the truly astonishing aspect is the data output. The LHC generates around 15 petabytes of data every year. To put this into perspective, 15 petabytes of data is equivalent to about 15 million gigabytes. This massive volume of information poses significant challenges in terms of storage, processing, and analysis. The data is generated from the millions of particle collisions that occur every second within the LHC. Each collision produces a wealth of information about the particles involved and the resulting interactions. To handle this immense amount of information, an international collaboration established a specialized computing grid specifically for the LHC. This grid, known as the Worldwide LHC Computing Grid, ULCG, is a network of over 170 computing centers in 42 countries. It is designed to store, distribute, and analyze the data produced by the LHC. The WLCG is a technological marvel, providing the necessary infrastructure to manage the LHC's data efficiently. The computing grid involves cutting-edge technology and innovative software solutions. Data from the LHC is first processed by the Tier 0 Center at CERN, where initial analysis and filtering occur. The filtered data is then distributed to Tier 1 centers around the world for further processing. Finally, Tier 2 centers, which include university and research institute computing facilities, conduct detailed analyses and simulations. This tiered approach ensures that the massive data load is managed effectively and that valuable insights are extracted promptly. The primary goal of the LHC is to uncover the secrets of the Higgs boson, a particle that was theorized for decades before being discovered by the LHC in 2012. The Higgs boson is essential for understanding why particles have mass. Despite its importance, the Higgs boson remained unseen due to its substantial mass, making it difficult to produce and detect with previous technology. With its immense power, the LHC can produce several Higgs bosons each minute during high-energy collisions. These collisions occur at nearly the speed of light, recreating conditions similar to those just after the Big Bang. The ability to produce Higgs bosons regularly allows scientists to study this elusive particle in unprecedented detail. By examining how the Higgs boson interacts with other particles, researchers can gain insights into the fundamental structure of the universe. The discovery and ongoing study of the Higgs boson have profound implications for particle physics. It confirms the mechanism that gives particles their mass, as predicted by the standard model of particle physics. However, the Higgs boson also raises new questions, such as the nature of dark matter and the potential existence of other unknown particles. The data generated by the LHC is crucial for exploring these mysteries. The quest to explore the unknown realms of physics with the Large Hadron Collider, LHC, can be likened to attempting to capture a rare, elusive creature, one that many believed existed but had never seen. The discovery of the Higgs boson was a monumental achievement, but the LHC's ambitions extended far beyond that. It ventured into uncharted territories of physics, probing for supersymmetric particles and other hidden phenomena that could fundamentally alter our understanding of the universe. The journey, however, was not without its challenges. Shortly after the LHC began operations in September 2008, a significant setback occurred. A magnet malfunction caused extensive damage to the collider, halting experiments and necessitating a shutdown for over a year. This incident underscored the complexity and delicacy of operating such a massive and sophisticated machine. The repair and recovery process was arduous, involving meticulous work to replace and recalibrate the damaged components. Despite this initial hurdle, the LHC resumed its operations from 2009 to 2013. During this period, the collider made several groundbreaking discoveries, the most notable being the identification of the Higgs boson in 2012. This discovery was a major milestone in particle physics, confirming the existence of the particle that gives mass to other particles, as predicted by the Standard Model. It was a momentous achievement that validated decades of theoretical work and experimental efforts. Following this success, the LHC was temporarily shut down in 2013 for a series of planned upgrades. These enhancements were designed to increase its power and improve its detection capabilities. The upgrades included strengthening the collider's magnets, improving its cooling systems, and enhancing the data collection and processing infrastructure. The LHC returned to operation in 2015, entering its second phase, which lasted until 2018. During this second phase, the LHC continued to explore new frontiers in particle physics. Researchers focused on searching for evidence of supersymmetry, a theoretical framework that extends the Standard Model by predicting a larger family of particles. The collider also investigated other exotic phenomena, such as dark matter candidates and potential extra dimensions. After another break for additional upgrades, the LHC resumed operations in April 2022. This third phase features an enhanced beam energy of 6.8 TeV, allowing for even more powerful and precise collisions. This increased energy capacity is crucial for probing deeper into the subatomic world and potentially uncovering new particles and forces. The current phase of the LHC is expected to continue until 2026, promising to deliver even more captivating discoveries. Scientists are particularly excited about the potential to find new physics beyond the Standard Model. This could include evidence for dark matter, insights into the asymmetry between matter and antimatter, and further understanding of the strong force that binds quarks together in protons and neutrons. The LHC's journey has been marked by both significant challenges and remarkable breakthroughs. From its early setback due to a magnet malfunction to the historic discovery of the Higgs boson and beyond, the LHC has continually pushed the boundaries of our knowledge. Its ongoing upgrades and current phase of operation hold the promise of even more revolutionary discoveries, continuing to captivate and inspire the scientific community and the public alike. But on July 7th, during its third run, something truly remarkable occurred. Picture Earth's magnetic field as a protective bubble around our planet. On that day, a mysterious crack appeared in the shield. This wasn't just a brief glitch. It remained open for an incredible 14 hours. Imagine a window left open on a stormy night, letting in the cold winds. This crack allowed a surge of solar winds from the sun, causing massive geomagnetic storms. The result: spectacular displays of auroras lit up the sky. Fans of Stranger Things might liken this event to the emergence of the monstrous Vecna, humorously suggesting he came through this crack. While that's just playful speculation, the breathtaking auroras were a real and undeniable visual treat. Think of the search for dark matter like a treasure hunt where, instead of finding the actual treasure, you uncover maps that lead to it. These clues might just be hints for more significant discoveries in future experiments. Here's an intriguing twist: dark matter. This mysterious substance, though invisible, constitutes a significant part of our universe. Some of the new particles detected by the LHC might be linked to dark matter. However, these particles are so elusive that they rarely reveal themselves directly. It's akin to trying to see the wind. You can't see it directly, but you can observe its effects, like leaves rustling in the breeze. At the LHC, scientists look for other particles behaving unusually, which might suggest the presence of these invisible ones. The challenge lies in the fact that these signs are often incredibly faint. Detecting them is like trying to hear a whisper in the middle of a loud rock concert. The subtle indications of dark matter are easily drowned out by more dominant signals. This makes the task of identifying dark matter particles exceptionally difficult. However, with the upgrades introduced in Run 3, the LHC's detectors have been enhanced to pick up these faint signals more effectively. These upgrades include improvements in sensitivity and resolution, allowing scientists to detect even the slightest anomalies in particle behavior. This enhanced capability increases the likelihood of capturing elusive particles associated with dark matter. These advancements mean that scientists are better equipped than ever to uncover new clues about dark matter. Each detected anomaly, no matter how small, brings researchers one step closer to understanding this enigmatic substance. The ongoing experiments and data analysis are crucial for piecing together the puzzle of dark matter, potentially leading to groundbreaking discoveries in future runs of the LHC. The search for dark matter at the LHC is like a meticulous treasure hunt. While the actual treasure remains hidden, the maps and clues gathered along the way provide invaluable guidance. The elusive nature of dark matter presents significant challenges, but with the LHC's upgraded detectors, scientists are now more capable of picking up the faint signals that could reveal its secrets. As research continues, each discovery brings us closer to unraveling one of the greatest mysteries of the universe. But wait, there's more. Plans are in motion for an even larger and more ambitious project: the Future Circular Collider, FCC. Think of it as the LHC's bigger, more powerful sibling. This enormous particle accelerator could come with a price tag ranging from 9 to 21 billion euros. However, not everyone agrees with this investment. Some argue that such a substantial sum could be better spent on other significant scientific endeavors. For instance, why not build a giant radio telescope on the moon's far side or launch a space-based instrument to detect gravitational waves? The proposed Future Circular Collider has sparked considerable debate within the scientific community and beyond. While many see it as the next logical step in particle physics, others question the return on such a massive investment. Critics, like well-known physicist Sabine Hossenfelder, argue that this colossal machine might not deliver the groundbreaking discoveries we hope for. It's akin to investing in an ultra-powerful telescope that might not reveal any new stars. They suggest that alternative projects, such as developing advanced telescopes or space-based detectors, might yield more immediate and diverse scientific benefits. Despite these concerns, the FCC represents an extraordinary leap in our quest to understand the fundamental nature of the universe. If built, it would dwarf the LHC, providing unprecedented energy levels and collision rates. This increased capability would allow scientists to explore uncharted territories in particle physics, potentially uncovering new particles and forces that could revolutionize our understanding of the universe. Meanwhile, the LHC is gearing up for Run 3, and even a potential Run 4, promising plenty of exciting science on the horizon. Each phase of LHC operations has brought us closer to solving key mysteries in physics, such as the nature of dark matter, the behavior of antimatter, and the fundamental forces of nature. We are in the midst of a cosmic detective story, piecing together clues one by one, with each phase promising new insights and discoveries. The Future Circular Collider represents both a bold vision and a contentious investment in the future of particle physics. While its potential to unlock new realms of understanding is vast, so are the costs and uncertainties associated with its construction and operation. As the scientific community continues to debate its merits, The LHC's ongoing and future runs ensure that our journey of discovery is far from over. We stand on the brink of new breakthroughs, driven by our relentless curiosity and the ever-advancing frontier of science. Think of these developments like episodes of a gripping series, and we're about to binge-watch the latest installment. One recent surprise involved an anomaly in Earth's magnetic field that stayed open much longer than expected. Imagine discovering a hidden door in your house you never knew existed. This unexpected crack in the magnetic field allowed solar winds to flood in, causing geomagnetic storms and dazzling auroras. What more might we uncover next? Max Laughlin, a prodigious thinker, proposes a rather alarming theory. He suggests that experiments at CERN could have caused a shift in our reality, leading to what is known as the Mandela effect. According to Laughlin, the high-energy particle collisions at CERN might have created a ripple in the fabric of space-time, nudging us into a slightly different version of our universe. The Mandela effect refers to instances where many people remember events or details differently from how they actually occurred. Named after the false memory of Nelson Mandela dying in prison in the 1980s rather than in 2013, this phenomenon is believed by some to be evidence of our transition to an alternate reality. For example, people might recall famous logos, quotes, or historical events differently than they are documented. Laughlin's theory posits that the extreme energies and conditions created during CERN's particle collisions could potentially disrupt the very fabric of space-time. These disruptions, he suggests, might result in our consciousness shifting into a universe almost identical to ours, but with subtle differences, hence the collective false memories. However, while Laughlin's theory is fascinating and captures the imagination, it remains speculative. The scientific community largely views it with skepticism. The experiments conducted at CERN are indeed at the cutting edge of physics, exploring the fundamental particles and forces that make up our universe. They push the boundaries of our understanding, but there is no concrete evidence to support the idea that they can create alternate realities or shift our consciousness into them. The work at CERN has led to numerous groundbreaking discoveries, including the confirmation of the Higgs boson, but its impact on the fabric of reality as we perceive it remains firmly within the realm of theoretical speculation. While the Mandela effect continues to intrigue and puzzle people, it is more likely a result of the complex workings of human memory and cognition than a consequence of particle physics experiments. With the emergence of various theories and public concerns about the experiments conducted at CERN, it's natural for people to worry about safety. One of the primary concerns at CERN involves radiation. To minimize exposure, CERN has implemented stringent safety protocols. Personnel working with particle accelerators and detectors are equipped with dosimeters, which constantly monitor their radiation levels. Areas where radiation hazards exist are strictly controlled, and access is limited to trained personnel. Additionally, the engineering designs of the facilities incorporate robust shielding materials to contain radiation effectively. Chemical safety is another critical aspect. CERN handles a variety of hazardous substances, and they have meticulous procedures for their handling and disposal. This ensures that chemicals are managed safely to prevent any accidents or environmental contamination. Electrical safety is also paramount, with regular inspections and adherence to international standards to prevent electrical hazards. Fire prevention systems are rigorously maintained, with regular drills and safety checks to ensure all equipment is functioning correctly. The safety of CERN's workforce is a top priority. Comprehensive training programs are in place to ensure that all personnel are well-versed in safety protocols. Safety drills are regularly conducted to prepare staff for emergencies such as fires, chemical spills, or radiation leaks. CERN also has an on-site medical service to address any health-related issues promptly, ensuring quick response times in case of accidents or medical emergencies. CERN is equally committed to environmental safety. They take significant steps to minimize their environmental footprint, managing waste responsibly and monitoring air and water quality to prevent contamination. CERN's operations include rigorous environmental monitoring to ensure that their activities do not adversely affect the surrounding area. CERN extends its safety commitments to the public. Access to the facility is controlled to minimize risks, ensuring that visitors are safe at all times. CERN maintains open lines of communication with local authorities and actively engages with the community to address any concerns. They hold public forums and provide detailed information about their safety measures to reassure the community and stakeholders.
Like I said, when Tesla said if mankind could understand the significance of 3, 6, and 9, they have keys to the universe. If they use it, the world changes in a beautiful way. If they ignore it, we cease to exist.
If humanity truly grasped the profound magnificence of the numbers 3, 6, and 9, they would unlock the secrets of the universe. What kind of hidden truths are we missing out on?
Remember Nikola Tesla said if mankind understood the magnificence of the numbers 3, 6, and 9, he would have the keys to the secrets of the universe. Like I said, when Tesla said if mankind could understand the significance of 3, 6, and 9, they have keys to the universe. Will you play that video for me, Jamie? Yeah, the linchpin bonding, it's the...
When Terrence Howard asked Joe Rogan to count the struts from the video he wanted to play, was he not challenging him to perceive the underlying complexities?
I think it'll be, well, there's 3 of them. Yes, that one right there. Now, before we play it, if you count the struts and watch how many struts bond as it becomes this right here.
Okay.
And just count it as it goes.
Terrence Howard breaks down the formation of the periodic table, shedding light on its intricate origins and inviting us to explore the profound implications of its systematic arrangement.
Just let it play. You'll see 1, 2, 3. And we know this is a magnetism because it's expanding in the center. Now you'll see 6 of these bonds. And those colors going across there is basically the periodic table. 5, 6, yep. And then the last one comes in, and now you have your 9.
According to Terrence Howard's take, magnetism kicks off from its center and spreads outwards, flipping our usual understanding on its head.
And this is magnetism. Like I said, magnetism expands at the center. So you have your 3, 6, 9, and it's back to that same fractal again. So now what you do, if you will do me a favor.
So when Tesla said that, what did he mean?
He was talking about these numbers, this interaction of these 3, 6, and 9. But this is all of them coming around the tetrahedron at 120 degrees. This is how they all behave, and this is the fractal because it keeps getting back to these 4 vortices.
Terrence Howard lays out an intriguing idea about the grand unified field, suggesting that by arranging a set of key elements, we might be able to predict all sorts of relationships. It makes you wonder, what kind of patterns could we uncover, and what secrets of the universe might they reveal?
But now I want to show you, after let this go again so they could see it, how all of this is the grand unified field put together. Now I want to show you electricity in this space, which will be the next one. And you'll see 5 linchpins bonding. And you'll see that it collapses the dodecahedron. And that's the release of energy, but it'll still make that same tetrahedral space. Watch. So when I talk about materials engineering, now being able to be manipulated, and you could see that the dodecahedron has been collapsed, and these other, because electricity is seeking higher pressure conditions. It's more dense, but we're back to and these 5 will keep bonding with other 5s, building predictable structures, not haphazard things. 4 of these will come together and make a larger tetrahedron, and then those will bond and make larger. This is Jesus walking on water. This is the proof in the pudding. They don't have this for their chemical engineering programs now. They don't need those models of just a ball and just that little rod anymore. They now have what's necessary. The carbon line is that yellow line in between it. And when we put this in the solar apex and replace the sun with it, it predicts every star on the galactic plane, the ecliptic plane, and the celestial plane. every single star, it predicts it. When we put groups of linchpin, it predicts entire relationships. So now, that's why I said the Heisenberg uncertainty principle is out the window, because now with this combined with the wave conjugations or with the mirror shapes, you can, whether it's expanding or contracting, we can now predict precisely where everything shall occur. And the linchpins I've included all of that into the AI for the linchpins. And the best thing about IBM and all of those other companies, Raytheon, taking my patent and making money off of it, since I have priority, since I invented it, I can now use any innovation that they've done off of my patent and not have to pay them a licensing fee.
Terrence Howard's possession of technologies surpassing any government on Earth is underscored by his exploration of the math loop, a concept that challenges established norms and hints at revolutionary possibilities.
There's no government on this planet that has the technology that I have or can outdo what I have, because you can't outdo the fractal.
How many people have you, I know you spoke at Oxford about this, but you didn't speak.
Yeah, they didn't. Oxford did something that broke my heart. 5 minutes before the presentation, they wouldn't allow me to have a screen and show my proof.
Why?
Oh, their computer was down. And I was like, well, you can use my computer. No, we have sensitive things attached to it. I just need the projector. I don't need anything else, because they didn't want me to go and talk about this. And that's why I went out there and said, hey, pull out your calculator. I talked about acting for a couple minutes, for 20 minutes. And then I was like, pull out your calculator. And I want you to enter the square root of 2 in there, and let's walk through this loop that is the square root of 2. I was like, let's walk through this, where the square root of 2 cubed is the same value as the square root of 2 times 2. And then when you divide it by 2 and cube it again, you get back to you take the square root of 2, 1.414213562373095. You cube it, it's 2.828427121746190. Divide it by 2, it gets back to 1.414. Cube it again, is back to 2.828. Divided by 2, back to 1.414. Here we're taking 1, 2, 3 big steps. We're dividing it by 2, and we get back to the same value as we had in the very beginning. That's a loop. That's x cubed being equal to 2x, which is equal to x plus x. That's an unnatural equation. And every quantum mechanics and quantum physics equation has that square root of 2 in there. We've been living in this lie, this fostered lie, for so long.
And what's the solution to that?
The solution is learning how to multiply volumetrically, how the universe multiplies. And I've already produced all of these things.
The foundation of all our math is built upon a two-dimensional projection. This fact alone has a big impact on how we approach and understand mathematics.
It does not move, does it linearly. It does not walk on. All of our math is based upon a two-dimensional projection. What they do in calculus, they will reduce the action of all things. They'll keep trying to reduce it down to one moment, because they believe Newton's first law that everything moves in a straight line, or everything is still until acted upon. They forget that everything is in motion, and that concert of motion is a necessity. They have to include all the other forces involved in order to have equanimity in their equations.
And so how, in a practical sense, does this affect mathematics?
Well, once we let go of Cartesian space and the 90-degree angles, well, picture this. Let's take another practical place. Look at a computer chip. It has all of these 90-degree turns on it, typically, where they run the electricity. Can you imagine running at 186,624 miles a second in one direction, and you hit a wall, and you've got to stop, bounce off of that wall, and then you pick up your speed and you bounce off the next wall, and you bounce off the next and next and the next and the next. How much heat are you building up? How much friction is being built up from the interference in comparison to if it was just spherical, just going around? It would build up no heat. And if you allow it to be spiral, which my patent was talking about, that first patent was talking about, you're able to utilize all that energy so you don't need the cooling systems. You don't need all of this loss or entropy. None of that occurs when you go by universal standards. That's all they have to do is follow what the universe does. We have the contractive side, patented, ready and available. We have the expanded side, patented, worked out already, ready and available. And we've got the Constitution between the two of them.
The calculator is suggesting something pretty mind-bending. While we think we're moving in a straight line, everything in the universe is actually expanding like a sphere.
The calculator right now is still saying that we're on a linear path. And it's just multiplying things in a compartmentalized space.
So by reductionist viewpoint, by breaking things down to simple numbers, that you really can't just do that.
You can try to do it, but it's like the piano. Remember the piano, the earlier pianos, they had, before they compartmentalized and everything was, remember that everything in the universe expands as a sphere, everything. Even music expands as a sphere. But what they did with the piano is they took all the 12 notes and then they just start them all over again instead of accounting for the expansion, that space. So you would never, if you're looking at the periodic table, you would never get to the titanium or to the rubidium or to the cesium because they would all keep it with just the 7 tones. They don't allow for the necessary expansion, so you don't have all of these other isotopes to use because they keep things here. You don't allow your child, nope, you're not going to get taller. I need you to stay just at 4 feet. That's the height. That's how high you can go. You will not be allowed to grow further. And we naturally keep growing and expanding out. So they have to allow that, but their math doesn't allow it because it believes in a 2-dimensional space. And remember, there are no 2-dimensional spaces because in order for anything to be perceived, it has to be measurable. And measurable needs 3 dimensions, but it actually needs 4. It needs your perspective. You are the 4th dimension. And that's what Walter Russell also talked about, that it was 4 things coming together. And that's what woke me back up. And I was like, 4 bubbles meeting. But he still believed in the idea of straight lines. He was still hemmed in by it. We know the world, the universe and the world is round, but we're still using flat principles to approach it.
The linchpin's remarkable feature is its transmedium capability, urging us to contemplate its mysteries. Our immediate focus, decoupling multiple components. What hidden potentials and transformative opportunities lie within?
Greatest things about the linchpin is it's also submersible. So one of the main points is, I'm about to build 5 smaller ones. The only thing that I'm missing right now, because we have built a ton of, we've got like 20 different prototypes that.
So when you say submersible, you mean transmedium?
No, like transmedium. They can go underwater.
Fly like these UAPs.
Yeah, but no, we can go underwater and be able to go now.
To maneuver through the water.
And be able to grab, they can identify where that gold is.
Oh, God.
And now they can go down and pull it up themselves without even informing the government about it. I don't need any of that other stuff. And I think that's why this has been suppressed. When I first took it over to Raytheon, I have these 2 test pilots, both colonels, been there for 30 years, one at Boeing, one at Raytheon. He said, the people at Raytheon said, let's see if he can keep it. They didn't know I had all these other patents surrounding it that they had no idea, but its usage, if they use it, the world changes in a beautiful way. If they ignore it, we cease to exist because we'll continue down this wrong path.
So do you think that intelligent life in all places of the universe has figured this out already?
If they're traveling here, they have, because you don't use power to go from one place to another. You decouple from the electric pull. You decouple from the Earth, and guess what? The Earth pulls away from you at its speed. You decouple from the solar system, it pulls away at its speed. You decouple from the galaxy, it pulls away from you. That's all you really need to do, but they didn't know how to decouple in 2 years, I won't need props anymore. I'll use molecular excitation, which is all inside of the patents that I've put in there.
In a striking reflection of their surroundings, the intelligent race mirrors the environment's response to opposition by pushing back, raising intriguing questions about the intricacies of adaptation and resilience.
That you can do that, or you can just, like with music, use a discordant tone. And those tones will push away. There's a particular tone that the earth is on. There's a particular tone, the key of A. It's 432 hertz, the Schumann resonance. All you have to do is have the opposite tone to that, and it will be pushed away from it. You don't, the same way a bubble at the bottom of the ocean doesn't use any energy to get to the top. But because it's completely in opposition to its environment, the environment pushes it away. That's what you do if you're an intelligent race. You can use an oar. If you're trying to swim across the ocean, you can get across there. But an intelligent species, like Alan Watts said, will use a sail. And they'll tack and make their way across. You use the energy. That's what judo is. It's supposed to be the Tao way, which is the Wu way, which is not forcing anything. And the Japanese just say judo in a harsher sense, but it still means using the energy of your opponent against it without expressing unnecessary energy. So you just use the equal and opposite forces of tones. You can do all of this stuff with tone. You don't need to use any electricity beyond creating the frequency. That's what the Beatles use, not the Beatles, the singing group, but those Beatles that they have in the Scarab Beatles, and those people that were doing those experiments with it.